Hi, welcome to the Signal Path. In this episode, we're going to talk about the science of thermal imagers. We're actually kind of spoiled of how ubiquitous these kind of thermal cameras have become. You can even find them in really small form factors that attach to your phone. And that's because long-wave infrared detectors and bolometers have become so inexpensive to mass manufacture. And in these little tiny modules, you can get many pixels, and therefore you can build fairly good thermal cameras. And the software, of course, helps with that. But I don't want to start from this type of detector, although we'll get there at some point. I want to go back about 3 decades. How did people build thermal imagers back then? Because they certainly did exist, and they were beautifully and remarkably complicated. And the amount of problems they had to solve is, in a way, much more complicated than what's in here. So let's go back in time and see what's that all about. There's a lot of cool science there. So that's not a thermal camera, this is a thermal camera. In fact, both of these units plus the power supply, all of that is required to do any imaging. Just look at the cable that connects these two together. Look at the number of pins that are in there. Absolutely amazing. They even send you one of these that's several meters long and weighs several kilos. And check this out. Look at that. How cool is that? Unfortunately, the display is a little bit damaged, but it still works. But look at this, just crazy. Of course, there's a floppy disk in the front and all the... Wow, it sounds terrible. And there's also connectors in the back that give you the video output if you want to connect it to something else. Even comes with a remote control, kind of like a VCR. So what's going on? Why are there two different units? And what's happening between these two? And more importantly, what's in here? Because that is the detector head itself. And why is it so bulky? Well, we really got to look at the theory of operation. So now let's talk about detectors. Now in the lab, we have used a variety of type of detectors in the past. Things like indium gallium isotope detectors for measuring optical power. We've used pin diode detectors that are used in telecommunication and a variety of visible light detectors. Now all of these are used in many different applications, primarily in telecommunication. But the issue in measuring thermal or heat energy from objects from their black body radiation is that you're looking at a very long wavelength in the orders of several micron, even up to 15 micrometers in the infrared light. That means that you have to engineer the semiconductor material to have a really small band gap energy in order to be able to absorb these really long wavelength, low energy photons. And that's if you want to build a photovoltaic or a photoconductive type of detector. As I said, that's very different from the kind of detectors that are present in modern flare cameras. Now, I found this interesting paper because it has a nice little timeline showing all the different invention of different kind of detectors here, which is nice. So if you look over here, we have something called a Mercury-Cadmium-Tellurite detector. I actually didn't realize that they were invented all the way back in the 1960s. I thought they were a little bit more recent. Now, if you look at this all the way up here, things like the bolometer FBAs or pyroelectric FBAs, focal point arrays, these are the kind of different kind of detectors leveraging a completely different phenomenon. Maybe we'll get to these some other video. Let's focus on the Mercury-Cadmium-Tellurite. So because you can play with the semiconductor combination materials here, you can engineer that kind of band gap that I was talking about. And then we can build some semiconductor stack that is sensitive to that kind of wavelength. Now, it's really important to note that there's a big difference between building a single detector and an array of detectors. Once you have an FBA, then things become interesting because you can put a lens in front of it and then you can image a scene like a regular camera would. And then the question becomes, well, how many pixels can you have? What's the resolution? What's the spacing between the pixels? What's the diffraction limit at this particular wavelength of light you're looking for? But really, the fundamental principle becomes just like regular optics, and there are no moving parts in these, and that's a huge advantage. With a single pixel, things are a lot more complicated. In fact, this camera uses a single pixel, and I want to show you exactly how that works. If there is interest in bolometers and pyroelectric FBAs and so on, I'm happy to get into those and explain how they work as well, especially since they are more modern. But today I want to focus a little bit on this Mercury-Cadmium-Tellurite, which is an MCT detector. And we want to look at the cross-section of the semiconductor material and how that is actually built. So I have two examples of it here, one over here and one over here. Both of these growths are done with molecular beam epitaxy, which is quite common technique for growing these kind of materials. And these are much more advanced and these are more modern perhaps than the very, very basic MCT detector. These are dual color, they call them, where they can capture more than one wavelength at a time. But the idea is really simple. What you're doing is that you're looking at a combination of mercury and cadmium, and by playing with the ratio of these two elements, you can adjust the band gap energy of the material you're building. And this itself is a recurring theme. By playing with different materials, that band gap energy allows you to be selective in what kind of photon energy you can absorb. And that's exactly what we want here. We want to capture these kind of 10 micrometer or multi-micrometer wavelengths of light. And the lattice structure for this one is tellurite, and you're just replacing the different atoms in there in order to put the mercury and cadmium in there. You play with the growth, and then you get the composition you're looking for the band gap you're looking for. They also dope this MCT with indium and arsenic to create that junction. So essentially what happens is that a photon enters over here and creates a whole electron pair combination. So a photon turns into an electron. That's of course photoelectric or photovoltaic effect, which is the fundamental principle of a lot of these detectors. And here it looks like the substrate they're using a cadmium zinc tellurite, and they have to grow this, and the lattice structure has to be compatible in order for these materials to be able to coexist together. And this is again a common theme in semiconductor growth in general. You can't just grow anything on anything because there may be incompatibilities between the materials, and then the whole thing breaks apart. And you have to be very careful with the purity of everything else. It looks like the bump here is at the top, so the photons would have to go around here in order to create a combination. I think it might actually be coming from the top. I'm not sure how this is assembled. Now at the bottom here we have a slightly more complicated layers in here. This is actually on a silicon substrate, and it looks like there's some additional interfaces, zinc tellurite and cadmium tellurite, in order to do the conversion in here. And there is our arsenic and indium. This is perhaps simpler in some ways, because this looks like it has a band to absorber, but this one doesn't. So this is actually compatible with building an array. So you can build these in a larger array configuration, and I forget which company makes these. But the idea remains. We're just basically engineering the combination of these materials, and there is our basic MCT detector. Now, just because MCTs were invented a long time ago, that doesn't mean they're no longer relevant. They're in fact quite relevant, and they're used in many different detectors. And these two examples are from Thor Labs, and you can see that they give you a wavelength, a sensitivity comparison of different models that they sell. Some of them are fairly narrow band, some of them are quite a bit more broadband, but they're all in these long wavelength infrared detectors. Now, because the band gap energy is so small of these detectors, they're also susceptible to generating a lot of noise. So you'd have to cool them if you really want to reduce their dark current. And cooling them can be a challenge, you can imagine, because you want to cool them as much as possible. You can either cool them with thermoelectric coolers down to, let's say, minus 30, 40, 50 Celsius, or you can cool them really, really hard using things like liquid nitrogen and cryo engines to bring them close to minus 77 Kelvin temperature ranges. In that case, the noise drops significantly. So just like a regular photodetector, you still need to build some kind of a biasing circuitry around it. And that's the same pretty much for any photodetector, because the fundamental operation is still the same. So the cooling of it is a whole other issue, and that's another part of this camera that I really wanted to dig into, which makes it really interesting. Now, generally, the first step in building circuitry for any kind of photodetector is to build a model out of that detector itself. And this is the same procedure used pretty much for any kind of photodetector. So if we have one, we can break it into some more fundamental components. We have the IPD current. That's the current we're actually looking for. That's the current that is created from the photons coming in and getting converted to electrons. And then there's a diode model, because we're dealing with a junction. And then there's the dark current. And this is our enemy. This dark current is random noise generated inside of the photodetector, even if there is no photon coming in. And that's the problem, especially when the band gap energy is small. And then we have the junction capacitance and shunt resistance and shunt series, and these are going to primarily affect our bandwidth. Now, in our situation, we're not caring so much about the bandwidth of the system. We're just trying to capture these essentially thermal energy to do a thermal detector. So if the bandwidth is really, really low, then you won't be able to have a very fast frame rate. But I think for general use, this is not a huge problem. And then we have the load resistance that we want to put the current that's coming out. So this I out is now a combination of our dark current and a combination of our IPD current. And of course, this is the part we don't want. And that's where it's going to go down significantly if we were to cool the detector. Essentially, eventually, at some point, you can reduce this to zero. Of course, you can never get to zero. But if you do, the signal-to-noise ratio for the detector becomes unlimited. And really, every photon that comes in becomes an electron that you can detect, assuming the rest of the system is noiseless. So now we can think about building a really simple biasing circuitry. We have a fairly low noise biasing circuitry generated here using a voltage regulator and a battery potentially, and then a simple RC filter. So here we're generating a really stable low noise voltage here that sits on one side of the photodetector, biasing it essentially, and then any photon coming in is going to generate the electrons, and those leave into a load. Now, this right away is obvious that this is an unamplified system because we have nothing amplifying these electrons coming in. So the voltage generated at this node can become quite small if the number of photons arriving is few. And therefore, that's not really how these are typically used. You really want that amplification. And you really want a low noise amplifier. And of course, for photodetectors, we're going to use a transimpedance amplifier, an amplifier with a feedback circuitry around it. And here's our photodetector, and we have two different kinds of biasing. You can ground it, you have a photovoltaic kind of detector, or you put a negative bias voltage for a photoconductive detector. Each has an advantage and a disadvantage. One gives you more bandwidth, one gives you less dark current, and all of these are possible for us to explore. And this is going to now create the amplification over here. Now we can put that into a load. So that's the real circuit that we want to build. Now this is very simple. In theory, there's more complications and therefore more advanced type of circuitry. But I think we should be able to build something like this, or at least use instrumentation to detect current from the photodetector. All of these circuitries are already built into our camera, of course, and we're going to observe them. So we took this little journey talking about detectors and circuits so we can appreciate the specification of the camera from its manual, so we can interpret it a little bit better. So first look at this, the spectral bandpass. So you can see that the camera comes in a couple of different models, sensitive between 8 to 12, 3 to 5, and 3 to 12 micron. These are exactly the long wavelengths we were talking about. And look at the detector, Mercury-Cadmium-Tellurite. That's exactly what we've been talking about. And check this out. They cool that detector to 77 Kelvin. So it's really, really cold. And they do this, of course, to reduce the dark current and the noise that we were just talking about. There's another interesting parameter we need to pay attention to, and that's the NETD, the noise equivalent temperature difference. Now, normally for detectors and sensors, we define something called an NEP, which is a noise equivalent power. And that tells you at what point does the power of the noise and the power of the signal in a 1 Hertz band become the same. And that should immediately intuitively tell us something, because it tells you at what point does your noise and your signal become roughly the same amount. So in this case, because we're talking about temperature detections, they define something slightly different, but the foundation is the same. This tells you what is the smallest temperature difference that you can detect because of the presence of noise. And it shouldn't surprise us that, look, if you average things, you get a much better delta. And averaging always means you're, of course, summing things and averaging, so the noise is adding up in power, whereas your signal is adding up in voltage. So you get some advantage by that averaging effect, and it gets significantly better. But how does this compare to something like our flare camera? Well, here's the E95 specification. First thing to note is that it has a lot of pixels. This is only a single detector. The other thing to note is the fact that this is completely uncooled, and it's a microbolometer, which is one of the other detectors that we didn't talk about. So uncooled is already a massive advantage. It makes everything so much easier. And look at this. Its NETD is pretty good, 0.04. So it's already better than this one. But again, don't underestimate MCT detectors. Modern MCT detectors that are cooled can become incredibly good, much, much better than anything else, especially if their surface area is large and you're capturing a lot of photons as well. The equivalent performance can be quite good. But right away, you can see how much of a difference there is between these two, and how difficult it must be to build this camera versus this one, just from the cooling and everything else that's involved. And that's going to be super interesting when we take the camera apart. So finally, how do we solve the fact that we only have one detector and we want to scan an entire image, an entire scene? Well, obviously we're going to need some kind of moving parts, and that's exactly what they do. It's also kind of crazy that they build things like this, because you'll see how complicated it actually is. So light coming over here has to hit multiple moving mirrors. One mirror is the vertical scanning mirror. This is going to scan our environment vertically up and down. And the light from that is going to bounce another galvanometer. This is the horizontal one, and that's going to scan our scene horizontally in the other direction. And both of these are moving simultaneously in synchronization, so that you can do kind of a scanning, kind of like a CRT in a way, right? The CRT is the exact opposite. You use magnets to scan a vertical, horizontal scene. This is using mirrors to do the opposite. Now the photons, when they bounce off of this and scan the scene, they come through here, they hit another mirror, go through some hole, hit another mirror, and then finally hit our detector, which is our MCT detector. But right away, you'll notice that if I want to scan a scene pretty fast, I would have to move these mirrors really quickly. In fact, you can see that the vertical mirror is running at 60 Hertz, but the horizontal is running almost at 4 kilohertz. So these mirrors will have quite a bit of inertia you need to overcome, and they're going to have a lot of resistance, air resistance, if you want to jiggle them at such a high frequency. So what do? Well, they put the whole thing in a cage, and they make a vacuum. So it's just crazy. Basically, you have to have these openings, which are going to have something like a germanium lens, which we will take a look at. Light comes in, the whole thing has to be under vacuum. The galvanometers, everything, the wires going in and out, just crazy. So this entire section allows you to now move these mirrors without any worry about the air resistance, and then going through, and it comes out and it hits the detector. So several really difficult things. This whole mirror mechanical vacuum system is quite difficult. The detector and the cooler of the detector that needs to go down to 77 Kelvin needs to also be built. All of that in that handheld unit. And that finally explains why it is so big and bulky. In fact, they divide the system like this. This is the head. That's the one with the handle on it, which we will take a look at. You can see that the thermal reference circuit is in here. The scanner is in here. The detector and the detector signal processing is in here. Everything in here is analog and mechanical. And that big cable with a lot of connectors we saw, that's this one. That is why it has so many pins on it, because it's doing everything in the analog domain. And then on the other side, we finally have an analog to digital converter. The scanner, driver, and servo controls are also over here. The switching power supply, the microprocessor, the scans and the measurement, the imaging averaging, LCD, digital. Oh my God, there's just so much here. Floppy disk and control panel. Everything is on that big box with the little display that flips over. So this is also a bit more complicated in the sense that there is actually a built-in lock-in amplifier that's in there too, which we will have to talk about. That's what the scanners have to be synchronized with the signal coming in. So yeah, a marvel of engineering, certainly in the 1990s or so, but there's so much cool science in here. Now finally, let's go take it apart or run it and see how it works, and then see if we can do something cool with it. So first thing first, let me see if I can address this LCD screen's problems, because it has a lot of lines on it and it's really in bad shape on the inside. So I'm going to try and see if I can take it out of this. I disconnected the cable and removed some screws, and I think that we should be able to pull this out. There we go. There's our entire LCD screen module. There we go. So we're going to open this and see if I can reach the other side of this. You can see all this discoloration inside. There are many, many lines on it. As long as I can get it good enough that we can look at the picture, that should be good. Well, this was a little bit of a disaster. So this thing had rust damage and adhesives were all broken apart. I think I did as best as I could. I can't, unfortunately, completely open the LCD because it's all glued together. They have glued all of these cables in as they're moving, and they wanted to make sure it doesn't become disconnected. Definitely not made to be repaired. But let's see if this has any better image. So I put the display back in there. You can see there are many different cards in here that perform various functions we saw in the block diagram. And here's the connector really nicely in the back. It's got two switches in the back as well. One that turns on the cryo engine so that it can maintain that temperature even if you're not running this, so you don't have to go through the cool down process. Some video outputs, but really legacy. I haven't been able to find anything that actually connects to it. Even has GPIB and some serial control. So I think we don't need to take this apart anymore. We should turn our focus and see if the whole thing actually works. And check it out. I think I got the display as good as it can possibly be. There's still one line left on it, you can see going vertically, but it does say the initialization has been completed. It did say it was cooling down for some time. I don't see an image yet. Let me see what happens if I push the image button. All right, let me remove the cap from the lens here. And let's see. Look at that. There's my hand. Thermal image. Let me adjust the range here. Wow, look at that. That's pretty cool. Yeah, so it works because how fast the frame rate is. This is mechanically scanning. I'd say that's pretty impressive. One of my fingers is cold, so if I put it here, and there it is. Yeah, you can see the individual veins. Let's just focus a little bit better. Look at that. Yeah, that's pretty incredible that something like this that is scanning mechanically with an MCT detector works as well as it does. I think that's really incredible. Just put some cold metal on my hand. Here's the lens cap. There it is. That's pretty cool. So the frame rate is really impressive. And I'm sure you can hear through the camera this really annoying high-pitched sound. That's the galvanometers that are moving around. There's also, I hear, a mechanical sound. That's the actually Stirling engine that is running inside as well. But it does work. It has a very, very large range of temperature that it can control. You can see I can adjust all that. It can read individual temperatures on the screen. Pretty amazing software considering the time that it was made. But anyway, we're really not interested in doing thermal imaging with it because it's really hard to use a device like this. I'm more interested in the detector itself. So let's take a look at it a little bit closer. It even has a color mode. That's cool. So now you can do something more similar to a typical thermal camera color gradient. Yeah, cool. Now, in fact, if we measure the sound coming from the unit, we can measure the frequency of the galvanometer because it's going to have this audible tone at the frequency that it is moving. So here we go. If I tap the screen, if I stop talking and look over here, there's a peak right there. And that peak frequency is 3933, which is exactly where it's supposed to be. So it all really works out. It is exactly running at that frequency. And check this out. The whole thing actually comes out as one unit, which is nice because we can analyze it much easier. Now, given that we've looked at the principal operation, we can identify the subcomponents fairly easily. Obviously, the infrared light enters over here, and this chamber over here, that's the vacuum chamber where the galvanometer and the mirrors are in. So the light goes in there, scans the field, and it comes up. It looks like there's another mirror in here, which then guides the light into the detector, which I will show you in a second. If I turn it onto the side, we can see some more of its features. For example, this is where they take the air out of this chamber. That's how they create the vacuum. And these are just some rubber stands. This is actually upside down. Normally it's on these two standing in here. This is reducing the vibration because remember there's a Stirling engine in here that's going to do the cooling down to 77 Kelvin. So the vibration protection here is pretty important. This board over here is fed with this. And this wire is connected to our MCT detector, which is inside of this tube, which I will show you in a second as well. So this is our analog processing, most likely a transimpedance amplifier, biasing, and so on, which is fed from this cable into the back unit over there. There's a whole bunch of moving parts in here as well. So for example, there's a chopper, as I explained. Here's a chopper. You can see I can spin it. So this is going to spin, and it's going to block the infrared light going into the detector at a certain rate. And there is a mirror in here on this side of it. If you look carefully, there's a mirror right there, and that mirror will periodically create a pulse on these infrared detectors. That's how they measure the RPM of this. And when they measure the RPM of this, that's going to become the lock-in amplifier's signal. That's where the chopper is coming from. Now it looks like there is another mirror in here, which is moved by this motor, and I think that might be a calibration where they just block the light and so that they allow the MCT to be zeroed out, I think, and this is controlled with this motor over here. And if you spin it on this side, this is equipped with a whole bunch of potential places to put filters. Now those filters are not populated in here, but that's controlled with this mirror. Everything in here has either an infrared detector for location or some kind of a Hall effect sensor. You can see there's a magnet in here. There's another one in here, and I think at some point there's two of them. There you go, there's two magnets right there. That's how it knows the zero position. So these two motors simply control that. The lens, of course, here in the front. And if I rotate it a little bit more, we have a couple of connectors in here which control the various motors in there. Spin it a little bit more, and the back is the main board, which interfaces with that really crazy connector. Over here, I actually installed this in here for the next experiment. I'll tell you, it's just a ground connection. This is a BLCD motor controller with 3 wires for the Hall effect sensors and 3 wires for the coils of the BLCD motor. And that is what is going to control the Stirling engine. Now, I've talked about in the video where I made liquid oxygen exactly how Stirling engines work and how they can reach that 77 degree Kelvin. To put it short, there is a closed system of gas that's moved back and forth, and that compression and expansion of the gas, followed by some really clever thermodynamics, gives you that really low temperature. This is a single-stage motor. So there's a whole bunch of other things for controlling all analog, all through-hole, nothing crazy. If I flip this on this side, we can see, oh, the lens just came off because it's not attached without the chassis very well. We're also blowing out the camera. There we go. Inside there is where the cable is going to the motor. So that's the motor interface, and that's going to go into our Stirling engine. So other than that, there's really not much going on. I think the principal operation is pretty straightforward. The chopper, the galvanometer, the MCT detector, and everything else, they work together. And if I flip it on this side, you can get a closer look. So this glass tube over here, the Stirling engine is on this side. The cold finger extends in there. And right in the front, at the end of the cold finger, is where we have our MCT detector. Now, there's one other subtlety in here. It's not enough to just run this because you want to make sure you have it in some kind of a PID controller so you know when it has reached the temperature you want it to be at. In order to do this, we need some kind of a temperature measurement as well that has to come from inside of that tube. And that's actually coming out over here. Right over here. This is a silicon diode of some kind, and they're going to excite it with a certain current, and they're going to measure that voltage, and that's going to tell us the temperature. Now, before we completely take this apart, I want to make some critical measurements to make sure that I understand, for example, at what voltage is this diode telling us that we've reached 77 Kelvin. So that's an important thing to measure. The second thing I'd like to measure is the reverse bias voltage on the MCT detector. I don't think it's a very large reverse bias voltage, maybe less than 0.1 volt. So we need to measure that, and we've got to be careful with that junction over there. The next thing we want to measure is to make sense of the wires of the motor. Flip this over here. Here's all the wires from the motor coming from here, and you can see that this chip in here is actually just a motor controller. So using some resistance measurements between these ports, we can identify all of its coils. So from that, we can also measure to see what's the voltage it's using for the motor, so we can see if we can drive it externally. With a couple of these measurements, we should be able to identify how to run the motor, the detector, and the temperature sensor in absence of everything else, because I don't want everything else in there. Now, the reason I'm going to take this apart is because I'm never going to use this as a thermal camera. It's just not very practical. But the MCT detector, as well as the cryo engine itself, can lead to some really interesting experiments, which I want to do in the future. I'll tell you a little bit about what I intend to do for it later, but I still want to get that thing to run as a standalone unit so that we can make that happen. Okay, so step one is to measure the excitation current going into our diode that's used for measuring the temperature, as well as looking at what voltage indicates 77 Kelvin. So I have everything connected, everything's turned off right now. This is going to measure our current, this is going to measure our voltage. Let's go and turn it on. Here we go. Let's see what we see. So it looks like the excitation current is about 450 microamp, which is quite high. Normally these kind of detectors have maybe 10 microamp, 100 microamp maximum through them, so it's a pretty high current. And we are seeing the voltage here, 0.7 volt. It kind of makes sense, and it is rising because it's cooling down. Of course, the engine is running now. So we're going to wait a little bit, and it's going to reach a point where the sound of the motor is going to change. It's going to drop the RPM of the motor in the Stirling engine because it's reached temperature. It's just going to try and stabilize it at that point, and then we'll record the final voltage there. So the motor has settled down and the instrument says we have reached 77 Kelvin, and we can see now the voltage required on our diode junction detector for that particular temperature. So that is the number we need to remember. And at the same time, I've switched this to the 10 amp range because I wanted to make sure that the burden voltage of this multimeter at the low current ports does not interfere with our measurement there. So that all looks pretty good. So we have all the information we need for the temperature sensor. Now, in order to monitor the cryo engine's motor wiring, I've simply brought them all out and I connected them to the 6 channels of the Tektronix 4 Series B. This allows us to look at all the signals at the same time, find the wires for the 3 cores and for the 3 Hall effect feedback sensors so that we can actually run it from a different BLDC motor driver potentially. So it's really nothing going on here aside from just monitoring all those wires at the same time. There's a 5 volt and ground as well, which doesn't need to be monitored. That's the power supply that runs the sensors inside of the motor itself. Let's take a look at the screen. All right, let's turn on the motor and see what happens. And here we go, quite familiar waveforms. So the first 3 from top to the bottom are the ones driving the coils inside the motor. And the 3 at the bottom are the ones coming back from the feedback. The 6 are all required in order to run a BLDC motor like this. Looking at these voltages, we have about 24 volts that show up on the coil. Kind of makes sense. And I was actually mistaken. These Hall effect sensors go to 12 volt. So the power supply I measured again is a 12 volt power supply. And this one is a little bit smaller. I'm not sure why one of the channels has a lower amplitude. Maybe it's something wrong with the circuit. Hopefully it's not damage from inside of the motor itself, but it seems to function just fine. Now this is when everything is cold. If I look at the frequency, it's running at 138 hertz. You can see 12 volt peak to peak for the Hall sensors, 23 and so volt peak to peak for the motors itself. Now we can let it run for a little bit of time and see what happens when it reaches temperature, because it's going to do some pulse width modulation and it's going to reduce the amount of power delivered. I want to see how the frequency changes in that situation. We need all this information to run the motor ourselves in the future. We can also observe the order here, so you can see that when this guy's peak stops, the one on channel 3 goes, and then this one goes. And we can find the corresponding Hall effect sensors by aligning the edges together, which I've already done and written down exactly what's supposed to connect to what. So from this sequence, hopefully we have reverse engineered the wiring. This is what happens after it reaches temperature. So there's a lot of modulation in each of these coils. Now you can clearly see the sequence there and how they're in order. Yeah, so looks pretty good. Now let's see if we can find something to drive it. And here's the cryo engine sensor assembly once it's taken out of the camera. I actually kept the main bracket where all these additional motors were connected to. I removed them because we don't need them. But the nice thing about this bracket is that it protects the tube. In a way, the actual sensor assembly doesn't include this bracket. And you can see that I have soldered some new wires directly onto it. I removed a really thin cable that was going to the MCT detector, and I soldered it directly to those pins, a coaxial cable now, which is terminated into just a 50 ohm load to protect it against any potential ESD event. Now keep in mind that when you solder cables and things to pins that are going through glass, you have to be very careful not to introduce too much thermal shock. So I preheated it a little bit, and then I did the soldering, and it was just fine. Here's where they take the air out of this. This entire thing has to be in vacuum. Look at how tiny and cute this thing is, that the Stirling engine and the whole assembly is just so small. And on this side of it, you can see some more features, particularly of the glass tube over there. You can see the cold fingertip. And at the edge of it, right over here, is where the glass ends. It's just a flat surface with a filter in front of it. That's where the MCT detector is. There's a mirror in here, so the infrared light going in there bounces against the mirror and goes this way and hits the MCT detector itself. There's also a lens in there, germanium lens, right over here, that focuses it onto that plane. So that's another reason why you want to keep this bracket, because it just makes the whole focusing much, much easier. In terms of driving the motor itself, I have a really simple brushless motor driver over here, which then takes the Hall effect sensors and the motor cores all in one. Pretty easy to use, nothing crazy. You can buy this very cheap these days, and it can run from a 22-volt supply. You can run the Hall effect sensor from 5 volt. It doesn't matter. This has 5-volt detectors anyway. You just have to figure out the cable order, which I did by looking at the waveforms on the oscilloscope earlier. And here's the end of the cable. That is the diode detector for measuring the temperature. You can see it's even labeled plus and minus. There's a whole bunch of other pins in there. I'm assuming that they're just not used, and that tube is something more generic, maybe to have more than one sensor or different types of it. And that's about it. Looks really nice. So now the question is, how do we put it in a bigger setup? There's also other components that I want to show you from inside the camera. And here's what is inside of the mirror assembly. Of course, there is no more vacuum because I removed the top cover and the front lens, but you can clearly see the two galvanometers. There's one over here and one over here, moving two mirrors. If I tilt this and look at it from the front, you can see the two individual mirrors down the middle. So this one at the bottom is moving this way and this one the other way, and the light bounces against this, and then it comes out of this germanium lens here at the bottom. Now these galvanometers need their own feedback, and if you look carefully, you can see at the bottom, if I can get this into focus, in the bottom there is a little emitter that hits the other side of this mirror, which has another mirror, and that bounces back on a linear photodetector, and that's how they figure out the position of this, making sure that it is within that. So basically, galvanometer is kind of like a servo, it has its own feedback. All the wires go through here at the end, which is all vacuum sealed on the other side. Really cool that just the length that people go through. You can see the other mirror in the back of this one. Here's the detector transmitter on this side. So one of them is paired here, the other one is paired on the other one, and this is a larger motor driver because this mirror is so much bigger. You can imagine if this thing is going to jiggle at 4 kilohertz, that the air resistance would be significant inside. That's why they have to remove the air from it. Yeah, really cool. You can still create vacuum in there because there's a port in here where you can take the air out. So it shouldn't be too difficult to do that again if you ever need to. But just looking at the effort, just the crazy effort that they must have gone through just to make all this work. Wow, incredible. Really cool to see what's inside. And here's the little chopper that they had made that sits between the optics and the detector. And yeah, it's very lightweight, and with the mirror in here, it can measure the RPM. Pretty cool. So how about another bonus teardown? Well, in my investigation, I also bought another old thermal camera that is built somewhat differently, even though the fundamental principle is the same. And this one comes with its own high-pressure gas canister. When I say high pressure, I'm talking about 5,000 psi. So what is going on here? So let me show you exactly how this one works as well, because it's really interesting. Now, removing the top cover, we see a whole bunch of electronics, and we can take this off. It's just processing the signal coming from the sensor. Then we have a cover, and then we can remove this cover as well. We already removed all the screws. And then inside of that, we see a whole bunch of moving parts again. There's actually a sensor in here. I've removed the sensor because I have to show you that separately. It's really cool as well. And this is solving the problem of scanning the field slightly differently. It has a rotating platform on its own brushless motor, which is also clever. On the surface of this, there are a lot of mirrors. You can see individual mirrors on it. Each of these mirrors, it has a slightly different angle. So it goes over the front. It's going to reflect that off of this mirror on this side, and it's going to go onto the detector, which used to sit over here. So they're basically scanning the field using a rotation. They don't need to create a vacuum in here because the air resistance with something like this is quite a bit smaller. It's clever too in its own way. And the advantage here is that because you're only doing a circular rotation, you don't have to fight an inertia of something that you have to move back and forth. So that's definitely easier to drive. The disadvantage is that you can only scan the field in one axis this way. So I think that they're using a linear array to cover the rest of it, or at least there's not enough mirrors in here for the resolution. So you have to have multiple detectors. So the alignment of these mirrors is quite difficult now because it all needs to land exactly in the right place onto the pixel, and that's the challenge. This thing over here was going through here and connected to the sensor. So what's going on over there? We have to talk about that. And here is the detector design from this other camera. Now, if you look at it from the top, and if you focus right here, you can see that it is indeed made of multiple pixels inside of that glass opening. And that makes the optics, the movable optics, quite a bit simpler. And we talked about that, and that's most likely why they're able to get away with as many mirrors as they have in order to scan the full scene with any reasonable resolution. Now, it also has many pins at the back, so therefore that's another indication that there are many pixels that are present. But the tube comes over here and enters it from this side, and the other end of this tube is where the canister is connected to. So if I pull this out, unfortunately this one is broken, and there's what's inside. Now, if you've ever seen one of these, you'd recognize it right away. This is a Joule-Thomson cryocooler, and this is a very interesting thermodynamic device in itself. So the really high pressure gas enters through here and it goes through this spiral, and at the very end it exits. And as soon as it exits, there's a huge pressure drop. We're talking about thousands of psi, a drop in pressure, and the tip is going to chill very, very quickly. And the return gas comes over here, and some of that actually cools the incoming gas as well. And with this technique, you're able to reach really, really low temperatures, like liquid nitrogen temperatures, 77 Kelvin. I actually considered using Joule-Thomsons in my liquid oxygen video, but it's very difficult to make these larger. You need a lot of pressure behind it. But for a miniaturized cooler, this works really well, and they're made today, of course, for these kind of applications. Now, we shouldn't be surprised about how this works, because it seems like it's not, where's the energy coming from to do this? But remember that this pressurized canister exists, and in order to pressurize this, a huge amount of energy has put in to create this multi-thousand psi of pressure. So the energy required to move thermal heat from basically the tip of this down this line already comes in from when it was used up to compress the gas in there. Because
in this house, we obey the laws of thermodynamics.
And check this out. Here's our setup based on everything that we have learned so far in order to see if we can make this cryogenic sensor work for us and detect some real infrared thermal signature. So we have at the heart of it, that module that I showed you, it's been taken out and put here on its side. So we have access to its window opening into the sensor itself. We need to drive the BLDC motor, which I have a little motor controller over here. These are really simple to drive because you have the 3 coils and the 3 Hall effect sensors, and then you can just have a simple driver with 120-degree encoding on the Hall effect sensors, and there you go, you can run it. Now we can run this from an external power supply. Here I'm using the Roden-Schwarz power supply, and we can adjust the amount of energy we put into the motor, which changes the lift of that motor in particular, and then we can adjust the temperature. Now remember that we need to measure the temperature and monitor it like we saw the actual system do. So I have it here connected to the M81 system. I recently did a full review and teardown of this instrument, so we're using it again here, both for its lock-in features and the many sources it has. We're using a current source to push current into the diode detector so that we can measure the temperature at the tip of our MCT detector. And at the same time, we're monitoring the voltage across the diode so we can find out when this thing has reached 77 Kelvin so we can adjust the power supply. Now, in a normal system, as you saw, this is in a negative feedback loop. So basically, it's constantly monitoring that voltage, and when it reaches the desired temperature, it's going to automatically change the RPM. Here, we're just doing it manually, but that doesn't really matter. It's really the same effect. Then at the same time, we need to bias our MCT detector and measure the current that comes out of it in the photoconductive mode. And we're doing that by using this current measurement input of the M81 system. Now remember that you can apply a bias to this, which is a huge advantage for these lock-in amplifiers. So we can bias the MCT detector at around minus 50 millivolt, which is what it requires. And that's going to allow us to measure the current coming out. So in this one setup, we are providing current to the temperature sensor, measuring the voltage of the temperature sensor, measuring the current coming from the MCT, the infrared detector, all at the same time. Now I'm using this voltage here at the top to create some thermal signature. I'll show you a closed-in zoom view in here in just a second, but this voltage comes over here, and there's a little resistor in here that sits in front of the window opening of our detector, and that is going to heat up and cool down. We're going to put a triangular wave in it, and that's going to create some thermal signature. And I want to know, can we actually measure that and see the triangle wave appear on the other side, which will be a huge thing because we're measuring the thermal signature of that resistor, which is a pretty cool thing. Now, of course, there's a lot of environmental effects of infrared and black body radiation around me, so I have a little encoder in here. It's going to be doing the chopping. So we also have a chopping lock-in amplifier going on at the same time, and that's going to constantly block that infrared light going into the sensor. And the reference signal of the lock-in coming from the chopper goes into the M81 system at the same time. And that's our whole setup. There's a lot going on here, but this is basically what that camera was doing, except that we don't have the mirrors that move the beam to scan the scene because we're only looking at essentially one small window. But this is a replica of what that camera was trying to do, which I think is pretty cool. And here's the close-in view. There is a resistor that's going to heat up and cool down, and it's going to go through the chopper, and that's the window opening, and it's going to bounce that way directly into our MCT detector. So pretty simple overall. Now keep in mind that if I move my hand in front of it over here, you're still going to chop the black body radiation signal from my hand as well. So when I'm running this experiment, it's probably a good idea not to sit in front of it because my movement are going to certainly be registered as well. In reality, you really want to isolate this section with walls that have very little black body radiation so that you're really focusing only on the beam coming in. But for the purposes of our test, this is good enough. This is going to get the point across. there's going to be some really interesting thermal inertia and thermal relaxation effects happening here as well, because as this is spinning, it's going to move air around the resistors. The resistor is going to cool down. We're going to try to heat it up. We'll see what kind of waveform comes out. This is a pretty cool test. Okay, step number 1, turn on the cryo Stirling engine to cool down the MCT detector. We're going to run it at 22 volts first. Let's take a look. There you go. It's burning at 3.5 watts. Not too bad. It doesn't need to do a lot of lift because the amount of energy it needs to take out in that tiny little area is pretty small, and maintaining its temperature in the vacuum shouldn't be too difficult. But there it is. You can see that it is burning a certain amount of power. Let's see if the temperature is actually dropping or not. And there you go, look at that. The voltage across the diode is rising, indicating that the temperature of the junction is dropping rapidly. Now, based on our experiment, we need to wait until this reaches about 1.035 volts or so, and then we're at about 77 Kelvin. At that point, I will back off the voltage on the driver, and it's going to stabilize to a steady state value around that, which is quite nice. It actually stabilizes fairly nicely. The amount of lift it needs is very little once it reaches 77 Kelvin, indicating that the sensor is in really good shape, the motor is working very well, and everything is in good isolation. So let's keep it going. And here we are. After only about a minute, we've reached our temperature. So I'm going to back off the motor here. All right, let's see. It looks like it's kind of stabilizing. Let's find the sweet spot for it to stay around this voltage. And we have stabilized around this with only 12 volt burning 2.5 watts. Not too bad. It's actually colder than 77 Kelvin, but it's going to be good for us to start the experiment. And here's the fun part. So let's see what we have here. So here's the settings of our M81. You can see 450 microamp of current is going into the temperature sensor. Over here, we're measuring 1.043, indicating below 77 Kelvin temperature of the MCT detector. At the bottom, I'm generating a triangular wave at 10 millihertz. So very, very slow triangular wave that goes up and down, heating up the resistor and cooling it down. And that's a fairly large amplitude, 10 volts. So I'm burning a lot of power in that resistor. So we can see a good amount of energy. Now, it's not damaging the resistor in any way, but I think it's getting over 40 or 50 Celsius. So it's still a fairly good dynamic range of temperature. And in the middle, we have our lock-in amplifier. This 79.9 hertz is the frequency of the chopper fed back into the reference input. Here's the bias voltage. It's right now disabled, minus 50 millivolt. And here's the current being measured in the radius of the current in lock-in mode. So first thing we do is we want to enable the bias voltage. So here's the bias voltage. We're going to enable the bias voltage. We're going to apply this configuration and turn this thing back on here. And there you go. Let it stabilize. There it is. So now let's see if we can capture a waveform. Now, because this is a very slow moving thing, we want to visualize it. So I've created here a simple recorder in the software where we're looking at the lock-in amplifier magnitude. That's going to correspond to the amount of long wave infrared signal hitting the MCT detector. And that's the current being measured at the same time. Here we go. Let's start that. And let's wait and see. There we go. You can see a little bit of noise on it going up and down. Remember, this is in nanoampere. And I don't know which cycle in the waveform we are in, but we're going to find out. Look, it's going up. That's pretty amazing. That's the resistor warming up. Now, when the resistor is running with a triangular wave of 10 millihertz going up and down, it doesn't matter if it goes below zero. The power consumption of the resistor is exactly the same. So essentially, we're getting a rectified version of the thermal signature. And look at it going up. It's not going to look perfectly triangular, of course, because we have thermal inertia, we have the thermal behavior of the resistor. It's going to smooth out this curve. It can change temperature very quickly. Very cool. Look at that. So let's wait for a while and see what it looks like. And check this out. Look how incredible this is. This is the waveform indicating the temperature of the resistor. And there is so much information we can extract from that. So at its hottest point, the current reaches 3 microamp, which is a lot of current. That resistor being around 40 or 50 Celsius is being certainly captured by the detector. At its coldest point, our current is fairly low, 185 nanoamp or so. And can you guess what these little spikes are? That's me walking in front of the setup. That's the black body radiation from my body summing on top of the signal coming from the resistor. Look how sensitive it is. Even in my little crude setup here, you can easily measure me just walking in front of it. And I'm not that much warmer than the environment. That's pretty amazing. We can also see something else. We can see that the resistor heats up faster than it cools down, which also makes sense. You can see that it cools down a lot more faster when it's very hot, also makes sense. Thermodynamically, it's going to release energy faster there, and it's going to smooth out at the bottom. And it's, of course, not going to look like a triangular wave because it's going to be low-pass filtered by the thermal inertia of the resistor. And it's just going to continuously go back and forth. It's working really well. Now, what happens if I change the frequency? Well, if I change the frequency and make it too fast, the resistor will not have enough time to cool down and warm up because it's going to just create a steady state temperature. We can try this out, actually. I can stop this, go back over here, go into our voltage source, and make the frequency 10 times higher. There it is. Now we can go back and apply that. Turn this back on. Now the frequency here, it should say 100 millihertz, and it does. We go back into here, and we're going to continue recording. And let's see what happens now. We give it a few moments here and see what the waveform looks like. And check it out, just like we expected, it reached a steady state temperature, and now the deviation is much smaller because we're just dissipating an average power, and the average power is going to be somewhere over here in its mean value, and it cooled down and reached there. So it all makes sense. We've made essentially a thermal low-pass filter using this little resistor and the signal we are applying to it. It's really amazing that all of this works as well as it does. So you may ask, why go through all this trouble, getting the sensor out, getting it to work with external circuitry and measuring and building a setup? Well, aside from the really cool science and exploring the engineering of it, the greenhouse gases also have very unique spectral absorptions in the wavelengths that this sensor works in. So I have some plans for detecting some of those things and being able to figure out the concentration of various gases using a setup like this. That's going to be for a future video. But this sensor is really valuable because it is a completely standalone. It has a built-in cryo engine. It's easy to interface with. You can measure its temperature. Really nice and compact. So it's a pretty cool thing to have. And there you have it. I hope you enjoyed this video and the extensive dive into the science and the engineering that goes into making such a thermal camera, as well as the experiment that I have put together. There's something really satisfying about this experiment because you can't make this work unless you really understand the science end to end. And that's one of the greatest joys in engineering, is this understanding the depth and the complexity and the ingenuity that's gone into building all of this. There's just so much going on in this one setup alone. As always, let me know what you think in the comment section, and I'll see you next time.